All right, let's dive in. Today, we're putting on our detective hats and taking a close look at a process that is absolutely central to the world of data: exploratory data analysis. You'll often hear it called EDA. Think of it as the essential first move in any data project. It's where we start digging for those hidden clues.
So, why are we talking about this? Well, this statistic right here is our first major clue: 80%. That means the vast majority of a data scientist's job isn't about building some super complex fancy model. Nope. It's about the foundational detective work, just getting to know the data you're working with. This is really where the investigation begins.
So what is EDA really? Well, it's pretty much what it sounds like. It's the whole process of getting acquainted with your data, you're summarizing its main features, a lot of the time with charts and graphs, all so you can spot patterns, catch anything that looks weird, and start forming some ideas before you even think about making any big decisions.
And this is the perfect way to think about it. You are a data detective. When you get a new data set, it's like arriving at a fresh crime scene. You wouldn't just rush in and make an arrest, right? Of course not. You'd survey the area, you'd look for evidence, and only then would you start piecing the story together.
Okay, so let's get our investigation started. The very first step for any good detective is to get a high-level overview of the scene, kind of like opening up the case file for the very first time.
Just a simple health check of our data can tell us so much. We'll use the famous Titanic dataset as our case file here. Right away, we see we have 891 passengers and 12 different pieces of information about each of them. But hang on, look closer. 866 missing cells? Whoa, that is a huge red flag. It tells us right from the get-go that our data is messy, and our investigation is going to have to deal with some incomplete information.
Okay, so we've surveyed the scene. Now, our detective moves on to the next phase: carefully examining each piece of evidence, or as we call it, each variable, one by one. This is what's known as univariate analysis.
Now, here's a crucial point. Not all clues are the same. We have two main types to work with. There are categorical clues, things like passenger class or gender, that basically put our data into different buckets. And then we have numerical clues, like a person's age or the fare they paid, which are actual measurable numbers. The type of clue we have totally changes the tools we're going to use to investigate it.
So for our categorical clues, the first question we always ask is about distribution. Simple, right? How many of our passengers fall into each category? Are the groups balanced, or is one group way bigger than the others?
And boom, a simple bar chart gives us the answer just like that. We can immediately see the distribution of passengers across the different classes on the Titanic. And look at that. The third class bar just towers over the others. This tells us that the vast majority of people on board were in the lowest class. That's a key piece of the story right there.
Now, what about our numerical clues like age or fare? We ask different kinds of questions here. We want to know the shape of the data. Where do most of the values tend to hang out? And, maybe most importantly, are there any outliers? Any weird values that just don't seem to fit in with the rest?
A histogram is our go-to tool for this. It's kind of like a bar chart, but for numbers. For the passenger ages, it instantly shows us this peak right in the young adult range, with fewer kids and elderly passengers. Just like that, we're starting to build a picture of who was actually on this ship.
The box plot is another one of my favorite tools. It's super powerful. It packs a ton of information into one simple shape, showing us the whole range of our data, and what's really cool is it helps us spot those outliers, those little dots that are way outside the main group. Imagine a ticket fare that was hundreds of times higher than the average. These are the strange clues that our detective absolutely has to investigate further.
Okay, so we've looked at each clue on its own, but this is where it gets really interesting. The real aha moments happen when our detective starts connecting the dots, finding relationships between different pieces of evidence. This is where the story truly starts to come to life.
Let's start with a classic example. We're going to connect two numerical clues. We'll switch our case file for a second to a data set of restaurant tips and ask a really simple question. Do people with a bigger bill tend to leave a bigger tip? Makes sense, right?
A scatter plot makes the answer crystal clear. I mean, you can just see it, can't you? Each dot is a customer, and there's a definite upward trend. As the total bill goes up, the tip tends to go up as well. This reveals a positive correlation, a clear connection between these two numerical clues.
But why stop at 2 clues? This is where we can go full-on Sherlock Holmes. We can layer even more information onto a single chart. Here, we can use color to show gender.
the shape of the dot to show if they were a smoker, and even make the size of the dot represent the number of people at the table. All of a sudden, one single picture is telling a complex, multi-layered story.
So what about connecting different types of clues? Let's go back to the Titanic. Let's connect a category, passenger class, with a number, the ticket fare. Did the class you were in have anything to do with how much you paid?
And the answer is a massive yes. I mean, just look at this bar chart. It shows the average fare paid by passengers in each class, and first class is in a completely different league. It's a stark picture of the economic divide on that ship. The visual makes that disparity impossible to ignore.
And finally, let's connect two categorical clues. This might just be the most important question in the entire Titanic story. Did your passenger class have anything to do with your chances of survival?
This simple table, which we call a crosstab, tells such a tragic story. Just look at the numbers for Class 3. Only 119 people survived, while 372 did not. Now compare that to Class 1, where more people survived than didn't. This isn't just data anymore. This is a powerful narrative about privilege and survival, and we uncovered it just by connecting two simple categories.
Now, going through all of this manually is fantastic for building your intuition, your gut feeling for the data. But let's be real. In the modern world, our detective has some pretty high-tech tools that can speed up this investigation dramatically.
There are programming libraries out there, like Pandas profiling in Python, that can generate a whole comprehensive report with just a few lines of code. They automatically do all the steps we just walked through: the basic stats, analyzing each clue, mapping all the connections, and even flagging potential issues like missing data. It's like having an assistant hand you a complete case file in minutes. But here's the crucial point, and if you take one thing away, let it be this. Whether you do it by hand, step by step, or you use an automated tool, EDA is the non-negotiable foundation of any good data analysis. You just can't skip it. It's like a detective trying to solve a case without ever visiting the crime scene. It prevents you from making biased or just plain wrong conclusions. This is how you build trust in the story your data is trying to tell you.
So the next time you get a new dataset, don't just jump straight to the end. Put on your detective hat, start asking questions, and find the clues. Because every single dataset has a story to tell. You just have to know how to look for it. What stories are hidden in yours?